Hey guys, so really excited to do this video today. So I was suggested that I get a mic, so I got one of those on Amazon, super cheap. So hoping that it makes things a lot better. And now this is a video that I've been wanting to do for a while. So one video that I've been wanting to do for a while is just like a live action homework problem solving video. So I've done some videos like this with me writing code, but those were without audio. Um, and so this is going to be the same kind of idea. So what I'm going to do today is I'm going to look at these quantum mechanics homework problems that I have to do, and I'm just going to just solve them first glance. Try to get some solutions here with you guys and kind of work through it out loud. I thought maybe that'd be cool. You guys can see how I'm thinking when I'm solving problems that I haven't already done, because a lot of my YouTube videos and especially the lecture stuff, I'm either doing derivations from a textbook that I've already gone through, looked at, or doing problems for classes that I already solved once. So now it'll be fresh off the cuff, mistakes bound to happen, but that's okay. I'm hoping this is kind of like a motivational kind of setup for someone that's wanting to get into math or physics or anything in STEM, to show that, like, it's a lot of trial and error, hard work, and maybe my process will give you guys some helpful tips. So this first problem we're going to do is, so we're in chapter 7 of my quantum mechanics textbook, which, if anybody is interested, the textbook is this one right here. It's a Modern Approach to Quantum Mechanics, the second edition by Townsend. And so chapter 7 for us is the one-dimensional harmonic oscillator. So I'm super excited for this chapter, and it's already been super cool so far. And so today in class, I bring this up because this motivates the solution that we're about to do. So before I do that, though, let's go ahead and state the problem. So we want to show that the constant C minus is equal to the square root of n. In other words, we have an eigenvalue equation where we have the operator A operating on the state n. And as of right now, we don't know how that eigenvalue turns out. So all we know is that we get some constant C minus and a new state n minus 1, because A is our lowering operator in this chapter. And so we want to show that this C1 is actually going to equal the square root of n. And so earlier in class today, we did a derivation for C plus, which has to do with the raising operator, A dagger. So here's A dagger, which is the adjoint of A. And we showed in class today that when you apply A dagger on the state n, you get the square root of n plus 1 multiplied by the n plus 1 state. And so we went through that derivation today, and Dr. Herman was just like, all right, well, do it for C minus for your homework. Go have fun, kids. And so I'll be honest, this is probably quite trivial in comparison to the one that we did in class today, which really wasn't that bad either. But there is, I will admit, I did read the problems prior to this video, but I did not make any attempts at all. I just was like, okay, how good are these problems? How much of a fool am I going to make myself look like? But one of them is going to be pretty tough. And I want to go ahead and say there's no guarantee that I'm getting the right answers here. For a problem like this, I'll hopefully know because they tell me what it's supposed to turn out to be. But for a lot of these, I'm just going to be giving it a solid try. And I won't know if I got it right until I get the homework back. But maybe I can do a follow-up video where I correct anything that I might have got wrong, or just tell you guys, hey, I did a good job. So let's go ahead and do this problem here. So the setup we're going to have is A operating on n gives us c minus n minus 1. And what we want to do is we want to go ahead and take this inner product with the bra, which is going to be the adjoint operator, a dagger, operating on the bra state n. And then on the other side, what that's going to give us is that's going to give us, now that we have in a dagger a n, and that's going to be equal to c minus times the inner product of n minus 1 bra, n minus 1 ket. So that's going to just be 1 because these are orthogonal states. We have an orthogonality condition such that if we have two of the same states, their inner product is 1. If we have two different states, then their inner product is 0. So this will just be 1. So then we'll have C1 on the other, or sorry, C minus on the other side. And now we have to do something a little tricky with this one. It's not that bad. Let me be careful. When we take the inner product, yeah, let me be careful here. See, this is, you gotta be careful, guys. So what we're actually doing on this other side is we're taking the inner product of the bra vector, which is actually n minus 1 with c minus star, because the bra vector is the complex conjugate of the ket vector. So now we have the complex conjugate of our constant c minus star. And so what we're actually going to have now is the modulus of c minus squared, because that's just a shorthand of writing c minus star times c minus. And then that's still multiplied by that inner product, which is going to be 1. So what we're going to have is we're going to have the modulus of c minus squared. That's equal to this left side. So what we're going to do on this left side is we're going to apply an identity. So earlier in the chapter, got it in my notes here, we defined this thing called the number operator n, that guy. And we said that n is equal to, find it here, we said that we were letting n equal a dagger a. And we also derived a relationship between n operating on n. Turns out it spits back out an n multiplied by n. So this ket vector is an eigenstate of the n operator. And so if you'll notice, hey, that's a dagger a. Hey, that's a dagger a. So now we can replace this with just capital N. And while we know how capital N operates on the n ket vector, it just gives us back an n times n. That's nice, right? And so because we have an inner product here, what's going to happen is when n operates on the ket vector, it gives us back that n. But then that's just multiplied by the inner product of n bra and ket, which just gives us 1. So now we have n equals c minus squared modulus squared. Well, then there's the answer, guys. We have some phase factor, e to the I theta times the square root of n. And for convenience, we can let our phase factor, we'll let theta be 0, which makes e to the I theta go to 1. And we get that c minus equals the square root of n, which proves our condition that when we operate with the a operator on our state n, we will get the square root of n multiplied by the n minus 1 ket vector. All right, that's a homework problem done. So I'm going to try to get, one more done. I got to go to work in about an hour, so let's see if we can knock out this next one. Now, I may have to erase a few times on this one because this problem's probably going to get a little long. So here's what we got. Now, what's convenient is we did derive something very similar to this in class today, so it shouldn't be too different. So what we want to do is we want to use the fact that the A operator acting on our zero state, or the ground state of the harmonic oscillator, is equal to 0. And that is true because 0 is our bottom state, right? And so if we apply our lowering operator to our lowest state, well, it can't go anywhere, so it's 0, right? Or that statement would, this wouldn't be the lowest state if the lowering operator can lower it. So that's 0. And then we're also going to use that if we take the product, if we sandwich the A operator in between the 0 state and the bra P, that then therefore also has to equal 0, because by definition this is 0. So if we just sandwich it with a bra vector, it's still 0. But now that's going to be useful. And so we're going to use that to solve directly for the ground state wave function, because these are just ket vector is not the same as a wave function, but you can get a wave function as an actual function from ket vectors. So ket vectors are used in matrix mechanics, which is discretized. And then when we get into wave mechanics, now we're using wave functions because we're in a continuous space, continuous function space. I'm actually writing my paper this semester on von Neumann's equivalence paper, where he showed an equivalence between matrix mechanics and wave mechanics, both being separate Hilbert spaces, and that you can map between them. So it's a little bit rigorous. I'm going to have to learn some functional analysis to do that paper, but I'm game, so we'll have some fun with that. Hopefully I can make a video talking about that as well. But anyways, back to this problem at hand. So what we want to do is we want to derive the ground state wave function in momentum space. So earlier today in class, we derived the ground state wave function in position space. Now we're going to do it in momentum space. So just to give us a bit of an idea of how this is going to run, and also to remind myself, we are going to be using this idea that we're using A, and we have defined A in terms of the position space operators X and P sub X, because we're in one dimension. We have defined A as the square root of m omega over 2 h bar multiplied by the operator, the position operator X, plus h bar over m omega, and the momentum operator P sub X. So that's what we're going to use. And so now what that means is we're going to operate, it's basically going to give us the ability to derive a differential equation. And then we have to solve it. So working right along to do that, we're going to see that we have this same thing, but now what we're going to do is we are going to write these operators in their momentum space representation. So in position space, the position operator x hat is just x, and the momentum operator in position space is, we're in one dimension, so d dx. If we were in 3 dimensions, it would be partial with respect to x, partial with respect to y, partial with respect to z, but we're in 1 dimension, so d dx it is. And so similarly, right, we have, oops, careful, there's an h bar over I on top of that d dx. And then we know that the position operator in momentum space, so now we're switching over, you'll notice this is kind of neat. They almost like switch roles, which makes some level of sense. But now the position operator in momentum space is I h bar instead of h bar over I ddp. Furthermore, and just like in position space, the momentum operator is just p. Cool. So where does that leave us? Well, now we replace this x hat with IH bar ddp, and we replace this over here with h bar over m omega p. And now we're going to operate that, because what we're effectively doing is we're taking this A operator and we're acting on P0. So what we're going to do is we're going to do exactly that. And so just to clean it up and make it look a little bit easier to see, we're going to say that P0 is just some function phi, and that'll help us see things a little bit. So now we'll just call that phi. In class today we used y, and now I am going to refer a bit to the derivation here, but not completely. So now what we're going to have is we can go ahead and take care of this constant, because we're going to let this thing be equal to 0, and that's because we're taking account of the fact that this is true. And so if we're operating A on P0, well, the operator only acts on the ket, not the bra. So that'll give us the fact that we're equal to 0, and then we can rearrange things and set up our differential equation. And so what we have now is that this constant can go away because we'll divide it out and it just goes away, it'll vanish. And so now what we have is we have IH bar phi prime plus h bar p over m omega phi equals 0. And so what we're going to see here is that now I'm going to rewrite this. Okay. I'm going to, first of all, clean things up a little bit. So I'm going to rewrite it as IH bar phi prime equals negative h bar p over m omega phi. Now I'm going to divide over this IH bar such that we have phi prime equals minus p over I m omega phi. Okay, so now we got that. And what I'm going to do now is I'm going to write this in a form to where you'll see that it's separable. So we have d phi dp equal to minus p I omega, I m omega, times phi. Cool. So now we're going to separate variables. I'm going to bring the phi to the bottom here, bring the dp up over here. So now I have d phi over phi equals minus P over I m omega dp. And now in order to solve this, I'll just integrate both sides. This is like the first solution technique you learn in differential equations. So if you've had differential equations, then you're super cool with what I'm doing here. And so now we're just going to follow this to conclusion. Now we should be getting a Gaussian, because we got a Gaussian for our position space wave function. And the position space and momentum space wave functions are related via a Fourier transform of Gaussian functions. And so if our position space wave function is a Gaussian, we better get a Gaussian for our momentum space if the Fourier transform is actually going to be how we're going to relate these things, which it is. So, and now that makes me curious. I feel like I could have solved this problem by just taking the position space one that I get and doing a Fourier transform. Maybe I'll come back to that. Maybe I'll come back to that, guys, and see if maybe that's another technique to solve this problem. So now what I'm going to do is this is 1 over phi d phi, which is the natural log of phi on the left here. On the right, I'll just write it out so everybody is cool with the steps. I don't want to skip steps. I'm going to factor out that constant of 1 over I m omega with a negative, and we'll just have p dp. And so you'll see we'll have natural log of phi is equal to minus 1 over I m omega, and then this is just going to be p squared over 2 plus some constant c. And now what I'm going to do is I'm going to exponentiate on both sides. So that'll cancel out my log, and I will have phi of p is equal to e raised to the minus p squared over 2im omega with some normalization constant n. And that comes from the fact that when I exponentiate this thing, I'm exponentiating both of these terms. So I'll have an e to all this stuff like I have up there, plus an e to the c, but e to the c is just another constant. E raised to a constant is just a constant. So I'll call that n, multiply it out, and there we go. So now the book tells me that they want me to normalize the wave function. And so the way that we would do that is just integrate it over space. And we can use a Gaussian identity in our appendix. And so I'll do that, and then I'll cut this video so it doesn't take 10 years to upload. So let's do that. So here's our momentum space wave function. And I am definitely going to see if the Fourier transform will get us right back there, because I do think that that would be fun. Quantum mechanics is so cool, guys. I am loving this class. I took a mathematical physics course last semester, and I also took a classical dynamics class last fall. And so I was introduced to Hamiltonian mechanics in the classical frame. And the whole time that we were doing Hamiltonian mechanics, my professor was like, this is going to be in quantum. This is going to be in quantum. And it's not the same, because in Hamiltonian mechanics, you have these things called Poisson brackets, which are these relationships between the partial derivatives of functions. So it has to do with this idea of these things not being commutative, or their partial derivatives aren't commutative, rather. So as you'll see here, I have the partial of q with respect to p times the partial of p with respect to q minus the partial of p with respect to q times the partial of q with respect to p. So these are just flipped around, but they're not zero. So it's not true that this product and this product are the same because you flipped the order. So that means that they don't commute. And so in quantum mechanics, you have commutation relations with operators. So like say we had two operators, A and B. You can't say in general that that's zero. You can show that it's zero for certain operators, and if they do commute, good. Certain things like if an operator commutes with the Hamiltonian operator, then it's time independent. Cool. Anywho, back to finishing this problem. I just erased my wave function. crap. Okay, let me see if I can remember it. It was e to the minus p squared over 2im omega with an n. Pretty sure that's right. Hopefully. Oh well, I'll just rewatch the video and catch it if it's not. So in order to normalize this thing, what we've got to do is we've got to integrate it over space. And so the way that we do that is we have to let's see, let's refer to this. So we'll have we're going to square this thing first. So we got to square this thing and integrate it over all space, because basically the idea is that we're doing phi, bra, phi, ket, right? Ooh, that's a little thing you don't want to miss. So in for my position space wave function, e to the minus m omega x squared over h bar, 2h bar. That's real. The exponent is real on that one. Here we have an I in there, so we're going to have a complex conjugate. So let's make sure that we're clean when we do this. So when we do this, we're going to get a modulus of n squared, because again, this n for the bra is technically n star, because it could be a complex number or imaginary or real. It can be either of them, so you got to be careful. And so that's going to leave us with e to the minus p squared over 2im omega times e to the p squared. The minus I will cancel that, minus, and we'll have 2im omega. And then we're just going to add those things. But now, wait a second. That's not good. That's going to give us 0, guys. Uh-oh, SpaghettiOs. That is not good. I'm sure you can see my anguish here. This is going to be e to the 0. Oh boy. Okay. Well, maybe that I shouldn't be in there. I don't know. All right. Well, I'm going to say no, it's not, and see what happens if it's not in there. So if it's not in there, then this is just going to be a minus again. And well, now that I think about it, I don't have an h bar. Like I said, mistakes were bound to happen. That's okay. I'm gonna try to solve the problem, post this thing on YouTube. I'll do another solution at another point when I solve one of these other problems and see if I can get it fixed. But maybe this is right. I don't know. We'll see. So now we have n squared, the integral over all space of e to the minus p squared over m omega, because that 2, when you add those, cancel. And that's with respect to p. And so this is a known Gaussian integral. So I'll go to my appendix here. I believe it's appendix D. I think so. Let me see. Here we go. Gaussian integrals. Okay, so if we have a Gaussian of the form minus ax squared, so if we have an integral with respect to a of the form e to the minus ax squared dx, where a is real. Ooh. So yeah, that tells me that I was not supposed to be in there, but I got to figure out a way to cancel it, because this this Gaussian integral identity only works if you have a real a value in your integrand. Mine was imaginary. Obviously, that gave me 0. So clearly, I wasn't supposed to be there, but I got to make sure I know why. So a step was wrong somewhere, but I think we're on the right track now. So this is going to end up evaluating to square root of pi over a. Okay. And so that means for me, A is equal to, well, where should I carry the negative? Well. I don't think you carry the negative in the answer because it's not there. So we'll say A is 1 over m omega. So that means we're going to get this integral is equal to n squared times the square root of pi over 1 over m omega. So we'll see this is a complex or compound, I forget which one it is, fraction, where this will flip up with the reciprocal. So we're just going to have square root of pi m omega. Cool. And that is equal to 1. I forgot. The way we normalize this as a normalization condition is that when you square this thing and integrate it over all space, the probability is 1, because these are wave functions of momentum probabilities. So now all we got to do is divide over. So it'll be n squared equals 1 over the square root of pi m omega. And so now we're going to have something in the fourth root, which is sounding about right because n for our position space was something in the fourth root as well. So we're going to have 1 over pi m omega raised to the 1/4, meaning our final phi of p momentum space wave function normalized is 1 over pi m omega to the 1/4 e minus p squared over m omega. And what we found for the other one was that it was minus m omega x squared over 2h bar. So, interesting. Okay, hopefully I haven't janked anything, but who knows? I probably did. I usually have to solve my homework problems once or twice because I make some silly errors, but hopefully you guys enjoyed. If anybody does figure out what I did wrong, Caleb Beach, if you're the same Caleb Beach I knew at Wake Tech, you could probably figure it out. Tell me what I did. But anyways, thanks for watching, guys, and I'll see you later.